Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, and welcome back to Physics with Beth and Beth. I'm Beth, and today we are continuing our discussion of AP Physics 1 Unit 6, which is on the energy and momentum of rotating systems. And so today, in this video, we're going to dive right into a new concept, which is the conservation of angular momentum. So as we've gone throughout this class together, we've talked about a few conservation laws in the universe, some of those fundamental laws of our world that everyone and everything has to obey. The first one was the conservation of energy. We talked about how however much energy you start out with has to be the same as the amount of energy that you finish with. Energy doesn't disappear, it's never created or destroyed, it is conserved, right? And then later on, we went to talk about the conservation of linear momentum, which similarly says that however much momentum we start out with, or our little p with a naught at the bottom, our initial momentum, has to be the same as the momentum that we finish with. Now, it turns out that there is a very similar conservation law for the universe that everything and everyone has to obey, which says that our angular momentum must also be conserved. So however much angular momentum we begin with is the same as the amount of angular momentum that we finish with. And this turns out to be a really handy rule whenever we're trying to solve a lot of physics problems. So a quick reminder that we calculate angular momentum by multiplying our moment of inertia by our rotational velocity. Now I want to talk about moment of inertia for just a little bit. Our moment of inertia is a number that describes an object's resistance to spinniness, as it were. It's a description of how hard it is to get an object to start rotating. So our angular momentum is equal to the product of how hard it is to rotate an object by that object's angular velocity. Now our resistance to spinniness has a lot to do with how far our mass is from our axis of rotation. So if I have a shape that has its mass more spread out, where my mass is farther on average from my axis of rotation, then it's going to be harder to get that thing spinning. It's going to have a higher moment of inertia. Similarly, if I have an object that's all squished in with all of its mass close to the axis of rotation, then it's going to have a low moment of inertia. It's going to be really easy to get that thing spinning. Are you following me? So let's talk about how we might apply these concepts with a little real world example. Let's talk about like an ice skater. So, whenever the Winter Olympics come around, I always love to watch the ice skaters, the figure skating. It's just a cool thing to see the people move so fast and far more gracefully than I could ever manage. But whenever you watch them spin and they're doing their little pirouette-y thingamabob, they start out with their arms farther out like this, and then they bring their arms in, and they speed up when they do so. Now, the reason that happens is because of the conservation of angular momentum. Their angular momentum has to stay the same, but they bring their mass on average inwards. They shrink the distance of their mass from its axis of rotation, which causes their moment of inertia to decrease. So if this has to stay constant and their moment of inertia decreases, then something else has to change to keep this number the same, which means that their angular velocity increases. So because their angular momentum stays constant, as they bring their arms in and decrease that moment of inertia, they start spinning faster. Then when they're done at the end of their spin and they throw their mass back outward in a big old grand show finish, they are increasing their moment of inertia by spreading their mass back out farther away from their axis of rotation, which helps them slow down and stop gracefully by decreasing their angular velocity. So let's talk about like a quick little practice problem with this. Let's say we have a merry-go-round that's spinning freely and a child walks quickly from the outside to the center along a radius. And now we're going to see how our angular momentum, our moment of inertia, and our angular velocity compare before the child walks to the center and after. So how does our angular momentum change? Well, kind of a trick question there. Our angular momentum is always conserved, so it doesn't change. So our angular momentum stays constant as we go throughout this process, as the child moves from the outside to the inside. What about our moment of inertia? Well, much like the ice skater just a second ago, as the child walks from the outside of the merry-go-round in towards the center, closer to that axis of rotation, they're changing the distribution of mass of the system, changing it from being more spread out, being farther away from the center on average, to being closer in, which means they are making it easier for the merry-go-round to spin. They're increasing the spinniness of the merry-go-round, as it were, which means our resistance to rotation is decreasing. Our moment of inertia drops. Now, because our moment of inertia drops, but we know our angular momentum has to stay constant, then that means that our angular velocity, much like the ice skater, has to increase in order to compensate. Okay, are you guys with me with all of this? Now, I could keep talking at you guys about this for like literally hours. You can just get me going on physics and I will not stop. But instead, let's work through a quick practice problem where we can see some actual numbers put to this, because sometimes it just helps to like get your hands around a problem to kind of see how it behaves. So let's go back to that little ice skater example I was talking about. Let's say we have an ice skater who has her original moment of inertia as a 5.0 kilogram meters squared when her arms are spread out. So she's spinning around and her arms are out, and this is her original moment of inertia. And she is spinning at 3 revolutions per second. Then she brings her arms in and drops her moment of inertia to her final moment of inertia, which is 2.0 kilogram meters squared. And now we're trying to figure out how fast she will be spinning at the end after she brings her arms in and drops her moment of inertia. So let's do that. Well, first of all, before we even get started, we should note the units that we have here. Revolutions per second. Those aren't our SI units, so the first thing we should do before we dive into our problem is convert this to the proper units. Instead of revolutions per second, we're going to want radians per second. So we're going to do a quick little unit conversion. I'm going to rewrite this as 3.0 revolutions per 1 second. We do our little train tracks. Well, how many radians do we have in 1 revolution? That's 2 pi. So I'm going to multiply this by 2 pi radians over 1 revolution. Revolutions divided by revolutions cancels out. I have 3 times 2 pi, which means we have 6 pi radians per every 1 second. And so that is our original angular velocity. Now, we know our original moment of inertia, we know our original angular velocity, we know our final moment of inertia, and we're trying to find our final angular velocity. Thankfully, we know that our angular momentum is always conserved, so if we solve for our initial angular momentum, which would be our I naught times omega naught, we know that that has to be the same as our I final times omega final. So let's find this product here. Let's solve for our initial angular momentum. So our initial angular momentum is just going to be these two numbers multiplied together, our moment of inertia times our angular velocity. So that would just be 5.0 kilogram meters squared times 6 pi radians per second, which is going to give us 5 pi times 6 would be 30 pi, which is about, if you multiply this out, 30 pi. We know that this is going to be equal to our final moment of inertia, 2.0 kilogram meters squared, times our final rotational velocity. So now when I solve for my omega final, then I'm just going to divide both of these sides. Why did I write that? That's not helpful anymore. Now I can just use this to solve for my final rotational velocity by dividing both sides by 2. I end up with that my final rotational velocity is 15 pi, which is kind of gross, so we're going to do multiplication and convert that. So my final rotational velocity is 47 radians per second, or 15 pi. Alrighty, that is all I have for you guys today. That was just a quick, short little practice problem on how we might use the conservation of angular momentum to solve a little word problem. We'll do more practice as we go forward. You guys will get plenty of practice applying this law because turns out it's a pretty important one. But thank you for sticking with me through all of this introduction. I hope to see you guys again, and happy physicsing.